Welcome to lesson number 6 and the bright line spectra. Our lesson objectives: differentiate between excited and ground state, explain how light is produced, and identify substances based upon their bright line spectra. When we talk about electrons, we look at the ground state. This is when electrons occupy their lowest available energy configuration or level. This is the configuration that's listed on the periodic table on the bottom of the element box. So for sodium, it's 281. 2 electrons in the first shell, 8 in the second, and 1 in the valence shell. What happens if the electrons don't occupy then this configuration? They occupy some other configuration which is higher energy. They are said to be in the excited state. So it's when electrons no longer occupy that lowest configuration, and therefore it's different than the one listed on the periodic table. So how do electrons get into this excited state? Well, that happens with the introduction of energy. So here's an example. Let's look at sodium. The ground state configuration on the periodic table is 281. So 2 electrons in the first energy level, 8 in the second, and 1 in the third. And so these are just some possible excited state configurations for sodium, and there are many more. So how do we get a 272 configuration? Well, if we introduce some energy, then maybe, let's say, this electron here jumps up to a higher energy level. It absorbed that energy, which moved it up to that higher energy level. And now we have 2 electrons in the valence shell, as listed here. And we have 3, 4, 5, 6, 7 in the second shell, and of course, still 2 in the first. The 263 configuration would occur the same way if it gave some more energy. Let's say maybe this electron here absorbs that energy and jumps to a higher energy level. So now we have 1, 2, 3 in that valence shell, and then 6 in the second and 2 in the first. And then 254 would occur the same way, giving more energy, and let's say getting this electron here to jump up to a higher energy level. So now we have 4 in the valence shell. And the closer we get to the nucleus here, the more energy it's going to take to move these electrons or excite them. And when they're in their excited state, such as the case as we are in right now, this is very temporary and unstable, and eventually the electrons will go back to their ground state configuration. And all that energy they absorb, they're going to give off in the form of light. So how do we determine then if the configuration that you are presented with in a question is the ground or excited state configuration? So if I gave you an example like 282, first thing I want to do is figure out what element is that. So I'm going to add up the total number of electrons in that configuration. So 282 is going to give me 12 electrons. That means 12 protons, which means atomic number 12. And so the atomic number 12 is going to be Mg. So I determined the element by doing that. If it matches the configuration on the periodic table, then we know it's ground state. If it doesn't match, then we know it's an excited state. So 282 matches perfectly, so we know that's an ground state configuration. So let's see some more examples. Identify the electron configuration as being ground state or excited state. So 261. So the first thing I want to do is figure out which element is this. So 2 plus 6 plus 1 is going to give me 9. I look up element number 9 because 9 electrons equals 9 protons in the neutral atom. And I see that's fluorine. And look at their configuration for fluorine. This is the ground state, the lowest possible energy configuration, which is 2 electrons in the first level and 7 in the second, or valence. And look at my configuration here, which is 261. It doesn't match, so we know that this is an excited state configuration. One of the electrons in this outer shell jumped up or gained energy and went to an even further electron level. Here are some more examples. So let's look at this first one here, 2883. I add that up, I get 21 electrons, which is the element Sc, and the configuration for Sc on the periodic table is the same as 2883, and therefore that's a ground state configuration, versus this one here, 2831, that when I add that up, I get 14 electrons, and that's going to be Si, which is silicon. And the configuration for silicon in the ground state is 284 on the periodic table, which does not match this configuration. So I know that 2831 is an excited state configuration. And it's important to note that in this excited state, the number or total number of electrons does not change. Just their location changes. So 2831 is 14 electrons, and 284 is still 14 electrons. Let's check your understanding then. Can you differentiate between excited and ground state? Now let's look at how light is produced due to the movement of electrons. As electrons absorb energy, they move from lower configuration to a higher energy configuration, which is known as the excited state. This is a temporary state and unstable, and eventually these electrons are going to go back to their ground state. And as these electrons fall back to their ground state, they give off that absorbed energy in the form of light energy. And we can see that light energy in the form of different colors. So a different color of light is determined by the amount of energy that the electrons are losing when they go back to their ground state. And so if they are giving off a small amount of energy, we're going to see that in the form of red light. And they're giving off a large amount of energy, we're going to see that in the form of violet light. And it creates this unique banding pattern, which is known as the bright line spectrum. So looking at it again in more detail, as these electrons absorb energy, they go to a higher energy level, and when they fall back down, they give off light. And we can see then that the amount of energy that they are giving off corresponds to a unique wavelength of light, which is shown by the color that we are seeing. And so looking at the whole electromagnetic spectrum, here is where visible light falls in this region, and you can see that connection between energy, wavelength, and color of light. And so the higher energy is going to be on the violet end of the visible light spectrum, and the lower of energy is going to be on the red side of the visible light spectrum. And because each element has a different amount of electrons as well as energy levels, it's going to produce different bands of light or bright line spectra that is unique to each element. It's like a fingerprint. And we can use this to identify unknown mixtures of gases. Because if you notice here, just in these examples, none of the bright line spectra match each other because they are all unique. And all of these lines correspond to electrons going back to their ground state configuration, so dropping from one energy level to the next. So for example, if you were asked what gases make up this unknown mixture, out of these four gases, which one, if any, are in here? Well, if any of the gases are in this unknown mixture, all of the bright line spectra of that gas are going to be in that mixture. So for example, we can see that all of gas A's bright line spectra is in our unknown mixture, indicated by the four bright line spectra lines, as we see here. And then we see that gas D, its entire bright line spectra is also in the unknown mixture. So this unknown mixture of gases contains gas A and gas D. So let's check your understanding. Can you explain how light is produced? And can you identify substances based upon their bright line spectra? At this point, you should be able to differentiate between excited and ground state, explain how light is produced, and identify substances based upon their bright line spectra.